Greetings. Welcome to the 8th lesson in a series of short lessons on basics of power systems engineering. This lesson covers the superposition principle in linear electrical circuits. Superposition principle allows analysis of multi-source linear circuits by considering the sources one at a time and adding the results. I will explain using the circuit on the next slide. Consider the circuit on this page. It has two energy sources, a current source and a voltage source. To explain superposition principle, we do not really need the values of the elements here. Suppose that we are interested in finding the current in a branch or a voltage between 2 points of the circuit. Superposition principle says that we can zero out all sources but one and find the quantity we are looking for due to the only source that's left active. Repeat the process for all remaining sources one at a time, and finally add all the results that were obtained for the quantity in question at each step, and this will equal the result with all of the sources active at the same time. As a point of discussion, let's focus on the current in the rightmost branch, I. What I can do as a first step is to zero out the current source and find the current due to the only remaining source, which is the voltage source. Here is the circuit with the voltage source alone active. Recall that current sources are zeroed out by replacing them with an open circuit. I have given the name I1 to the current due to the voltage source alone in the branch in question. Next, I will restore the current source and zero out the voltage source by shorting it out. Calling the current due to the current source alone I2, superposition principle says that adding I1 to I2 will give you the correct value for I. So for multiple source circuits, we can divide and conquer by considering the sources one at a time and adding the results. So here we find I1 due to voltage source alone, I2 due to current source alone, and then we add them together to find I from the original circuit. Let's put some numbers on this circuit and find the current I with the use of this technique. In this circuit, I'll first zero out the current source and calculate I1. Let's find the resistance seen by the voltage source. These two resistors are in series, adding to 525 ohms. Then the 525 ohm will fall parallel to the 40 ohm resistor. Once we find the parallel combination of the two, we'll add this 2 ohm resistor to it to find the equivalent resistance that the voltage source sees. I have it in this equation, 25 plus 500 for this branch in parallel with 40 and in series with 2. The equivalent resistance comes to 39.17 ohms. The current through the 2 ohm resistor is found next with the use of the Ohm's law. And that means dividing the voltage, 40 volts, over this equivalent resistance, 39.17, and the current through the 2 ohm resistor comes to 1.021 amps. I1, which is what we're interested in, can now be found using a current divider at this junction. The current going through this branch is multiplied by the resistance of this branch time over the sum of the resistances of these two branches, 525 over 525 plus 40 times the current coming to the junction, 1.021, gives me the current that goes through I1, and that's 0.9489 amps. I will next zero out the voltage source in the original circuit and find I2 due to the current source alone. Here we have the circuit with the voltage source taken out, in other words, replaced with a short circuit. 8 amp current that comes into here is divided between two branches here. One branch consists of these three, and the other branch is the 500 ohm. Again, we can use voltage divide or current divider to find the current through this branch, the 25 ohm branch. So first we'll find the equivalent of these three resistors. We have 40 and 2 in parallel, and then their total is added to 25 to give us 26.90 ohms for these three, 26.90 ohms. And now that we have the overall resistance of these three together and the one for the other branch, the current coming here as 8 amps is going to get divided between these two. The current through the 25 ohm branch equals the other resistor, the resistance of the other branch, 500, over the sum of the 500 and the 26.90 times the 8 amps that's being divided. So 8 times 500 over 500 plus 26.90 gives me the current through the 25 ohm resistor, and that comes to 7.592 amps. This current, the 7.592 amps, is further subdivided between the branches, the branch with the 2 ohm resistor and the branch with the 40 ohm resistor. And again, we can use the current divider formula to find the current through the 40 ohm resistor, which is what we're looking for, the I2. So again, we take the current through here, 7.592, multiply it by the fraction with a numerator of 2 and denominator of sum of the 40 and the 2. And we can see that I2 comes to 0.3615 amps. Adding the two currents I1 and I2 will give us the current that the original circuit will cause to flow in this branch. So that's done next. I equals I from the original circuit equals the I1 and I2 that we found earlier added together. And the result is 1.310, which is the answer here. I equals 1.310 amps. I would like to take a short break here and introduce myself and my work, after which I will continue the topic of this lesson, working out another example, this one with 3 voltage sources in it. My name is Fuad Albandi. I'm a PE in electrical engineering, licensed in the state of Maryland. This is the 8th lesson in a series of lessons on basics of electrical power engineering that I have published on the YouTube. You can see my name and email address on this page. You can visit my website at this link, own-your-destiny.mylearnworlds.com, for comprehensive modules on important topics in power systems engineering. I will now continue the lesson with example 2. In this example, we have 3 voltage sources that have the same open circuit voltage of 50 volts each, but they have a slightly different internal resistances, 1 for one of them, 2 for the other, and 1.5 ohms for the third one. These sources are connected in parallel and are powering an 80 ohm resistive load. We're asked to find the load voltage using the superposition principle. In other words, we are looking for V sub AB in this circuit. I'll keep the sources active one at a time and calculate the load voltage for each. Once we have calculated them for all 3 sources individually, we will add them to get the load voltage for the original circuit. Here is the circuit with only the left voltage source active and the other 2 zeroed out. We can see that the equivalent resistance seen by this source is going to be the parallel combination of these 3 resistors added to the 1 ohm resistor. You can see the equation here. 2 and 1.5 and 80 are taken in parallel, and their equivalent is added to 1 to get the equivalent resistance seen by this 50 volt source, and that equivalent resistance comes to 1.848 ohms. Now dividing 50 volts by this equivalent resistance gives the current through the 1 ohm resistor here. And I've done that here. 50 over 1.848 gives me 27.06 amps going through this resistor here. Now if I multiply this current by the resistance, which is 1 ohm, it will give me the voltage drop across this resistor. Plus or minus is going to be 27.06 volts, because I'm just multiplying it by 1. And then to see what the voltage across AB is, we'll just have to subtract 27.06 from the 50 volts because of the direction of this voltage here. The polarity is opposite of the 50 volts, so we have to subtract 27.06 from 50 to get the VAB here. And that's done here to get VAB, and it came to 22.94 volts. Well, let's call this voltage V1, and I have recorded it here. We will now work with the circuit that has only the middle source active, and that's this one. Again, looking for the equivalent resistance that's seen by 50 volt source here, we'll see that these resistors, the 1, the 1.5, and the 80 ohms are in parallel, and then their equivalent is in series with the 2 ohm. So we'll need to, well, I'll go over the equation here. 1 in parallel with 1.5 in parallel with 80 added to 2 gives me 2.560 ohm for the total equivalent resistance. And now dividing 50 by this equivalent resistance will give me the current that goes through the 2 ohm resistor, and that is 19.26 amps. Again, multiplying this current by the 2 ohm resistor will give me the voltage drop here, which I can then subtract from the 50 to get the VAB for this case. And that's done here. 50 minus 19.26 amps times 2 ohms gives me 11.47 for VAB. And let's call that one V2 and record that here. And finally, I will simply zero out the other two voltage sources and keep the third one open or active. Here the equivalent resistance is the parallel combination of the 1, the 2, and the 80 added to 1.5, and that's shown here. The equivalent resistance is 2.161 ohms. To find the current, I'll divide 50 by this resistance, and the current through the 1.5 ohm resistor comes to 23.14 amps. Once again, multiply this current by this resistance and subtract from 50 to get VAB again. And this time VAB comes to 15.30 volts. We'll call that V3, seen here. To find VAB of the original circuit, we will simply add these three voltages. VAB equals V1 plus V2 plus V3, which comes to 49.71 volts. We have reached the end of lesson 8. This is Fuad Albandi, founder and instructor of the educational group Own Your Destiny. If you enjoy watching my channel, please click on the subscribe button. You can also visit my website at the link shown here. Thanks for watching the presentation, and I hope to see you in another one of my presentations in the future.